Okay, quick mic check. Can everyone hear me?
Yes.
Awesome. Okay. Give me 1 second. Just gonna tweak one more thing, and then we're ready. Okay, let's get started. So just a quick check. Is this where we left off, or did we finish the slide already?
We did this.
Okay. All right. So let's go ahead and continue here. Looking at the value of K itself, capital K. The larger the value of K, the more it leans towards the product side. So remember, the value of K is a constant. So once you reach it, you can't really change that value. It is set where it is. Okay. But once we reach equilibrium, whatever the value is, if it happens to be a large K, that means at equilibrium, I have more products than I do reactants, or I have less reactants. It's pretty much the same thing. Now, if I have a smaller K, that usually indicates that I have a larger amount of my reactants, very small amount of my products. Any questions? Okay. So we're going to learn about a thing called the reaction quotient Q. So when something is at equilibrium, that means it has already reached the state that it needs to. But a lot of times in reality, we are never at equilibrium. This is not chapter 24, this is chapter 17. So 24 was included inside of chapter 16. So when we talked about nuclear chemistry for a bit, then we branched out of it back into chapter 16. Okay, so really quickly, the reaction quotient Q is what we use for whatever condition we have at that moment, because we're never always at equilibrium. Give me 1 second. Okay, sorry about that. Okay, so once again, the reaction quotient is wherever you are at that moment. So it doesn't necessarily mean that we are at equilibrium. So if the reaction quotient happens to equal K, then we are at equilibrium. Sometimes Q can be less than K or greater than K, whatever the situation. And we function the same exact way. So if we look over here, it is still written the same way. So it is always products over reactants. And whatever your coefficient is, always ends up being your exponent. Any questions? Okay. So let's give this a try. I want you to take these three equations here, and I want you to write down the QC, or in other words, just the reaction quotient. So set up the equilibrium expression for me. I'll give you some time with this. Okay, does anyone else still need more time with this? Okay, just really quickly, does anyone else still need more time with this? Seems like everyone's done. So I'm going to challenge you. If you finish really quickly and you thought it was really easy, I would go back and double check. So the first thing you want to do here is you want to go ahead and balance the equation. And that's always true for all equations. So if you didn't balance the equation, you're not going to get the correct answer at all. So out of curiosity, how many of you did not balance the equation? Okay. So once again, you always want to balance the equation. Once you are done balancing the equation, you can then go ahead and put in your coefficients as your exponents. Anyone have any questions on how this is set up?
Professor, question.
Sure.
So we did not take account solids and liquids while we were writing the reaction quotient?
That is a very good observation. So if you look right here, if you notice here, we didn't include any of this. So we're going to talk about that in a little bit, but solids and liquids are not included in our equilibrium expression. Only gases and aqueous solutions.
Okay,
That's a very good observation that you made. Okay. Does anyone else still need more time with this before I move forward? Okay, give you a little more time to copy things down. Okay. So we're going to talk more about the different forms of K, or we can refer to it as Q as well. So different ways that we can write this equilibrium expression. So we have one where we consider it an overall reaction. So just like our reaction mechanism, you have different steps. You have step 1, step 2, step 3. We assume that each one of those has a K of its own. And then when we multiply them across with each other, we get the K overall. So this can be done with a reaction mechanism as well. Another example that we have is when I go ahead and look at the relationship between the forward reaction and the reverse reaction. So if I said A changes into B, normally I would write this expression as B over A. If I wanted to look at the reverse reaction, the opposite side, if I wanted to flip it, this can be A over B. So if this is my K, A over B is essentially 1 over K. Yes.
So basically, Professor, what you're saying is that if it's like, if it's an equation that can't be reversed, it can still be the same thing?
Not exactly. So we are assuming this reaction is reversible, right? So A is changing to B, B is changing to A.
Oh,
When you write this expression here, if you write this
Okay.
K itself as your B over A, so it's kind of the reaction you have here. If I switch the equation and I wrote it like this, B over A,
oh,
then it
just,
just becomes this. And that's essentially
Oh.
related to the original K.
oh, okay. All right,
Okay.
thank you so much.
So this is still an expression of K. This is just 1 over the original K. Does that make sense?
Yeah, that does. Thank you.
Okay. Another example I have is when we go ahead and look at the value of the exponent. So if I have K here, and this was K to the n power, I assume that I go ahead and increase all of these by the n power. That's the same as if I wrote for this A right here. So instead of just writing A, like a little a, I put an n right in front. So I'm multiplying that amount. So remember, my coefficient becomes my exponent. So it functions the exact same way. Does that make sense? Or is anyone confused about this?
So basically, it's just whatever comes before it is going to be the exponent in the end?
Kind of like that. So if I look at this equation again, right? B
Yeah.
over A, this is equal
Yeah.
to my K, okay?
Yeah.
If I put a 2 in front of here and a 2 in front of here, that becomes B squared over A squared, which is the same as K squared.
Oh,
make
okay.
sense?
Yeah, that makes sense. Yeah.
So that's what our N represents for each one of these scenarios.
Okay. All right, thank you
Okay.
so much. Yep.
All right. Does anyone still need time with this before I move forward? Okay. So I want you to go ahead and take these two equations. We are going to go ahead and look for the overall equation first. Okay. Using that information, look for the overall equation. Okay. By now, everyone should be done with this one. So let's take a look at what we have. So we can go ahead and separate them as individual reactions. So if I just went ahead and I solve for Q1 by itself, I can get this expression here. Q2 by itself, I can solve it like that. Okay. If I wanted to multiply these two directly like this, it also works. Q overall is the same as if I just went ahead, canceled out things on both sides. So if I went ahead and just wrote down Q overall, I get this equation right here, put it in down. If I look at Q1 and Q2 individually, now I want to put these together. If I multiply these, you can see that the NO squared and ono squared shows up on both sides. So I can cross those out. And then all I have is whatever's left over on this side. So either method gets you the same answer. Does that make sense? For the second quiz, I actually didn't get a chance to fully check all of it. I'm doing another round of checking, so I did not finish that one. Okay. Okay. Once again, same details, nothing different here, just exactly what I mentioned. We cross out things that show up on both sides, top and bottom, and you get the same expression as your overall. And then we don't really need to know the second one. All we did was just increase the, we go ahead and multiply the two numbers. Next week's quiz is going to be on 16 and 24. So it's not going to include 17. 17 is the week after. 16 to 24, even though there's two different chapters, they function the same way. So I counted them as one chapter. But generally speaking, anytime you have a quiz, it's always going to be on one chapter only. Okay. So now I want you to do the same thing that you did before. Go ahead and take this expression that you see right here. This is the synthesis of ammonia. We will be using this a lot. So I want you to be familiar with it. This Kc value for this equation is this value at 1000 Kelvin. Given these expressions, write this in relationship to the original Kc, this value here. Okay, and then get me an answer. Okay, is anyone else confused about this? Let's say two people are confused about it. All right. So if this equation right here is my k, okay? I want you to compare that equation to the one on the bottom here. How are these two equations related? By a difference of what? By a difference of a third, right? So if I go ahead and multiply this by 1/3, it becomes the same thing down here. Divide this by 1/3 gives me the actual H2. This 2 divided by multiplied by 1/3 gives me 2/3. Does that make sense so far? The relation between these two is a difference of 1/3. If it doesn't make sense still, let me know. Okay. So the difference between these two in terms of its coefficient is a 1/3 difference. So what that means is when I'm writing my equilibrium expression, it should be to the 1/3. Does this part make sense so far? Okay, so that is pretty much it for this one right here. Whatever your k value is, take that to the 1/3 power and you will get the same answer. So this thing is going to give you 1/3 of the original k. Now, if I look at this one, it's a little bit more different. If you look carefully here, you have, this is essentially 1/2 of the original. So each one of these is divided by 2. But in addition to that, look at where your NH3 are. So this equation is flipped. So not only are we writing, let me go ahead and just clear something real quick. Okay, so not only are we writing this to the 1/2 power, this entire thing is 1/. Does that make sense? If you did k divided by 3 like this, it would not make sense. If we're referring to this one right here. 1/3 power, 1/3 essentially is the same as if you wrote 1/k. So this is just the cube root essentially. So the reason why we put this one as 1/, is because this is flipped. So the reciprocal is 1/k. So you're still solving for a k, but this is a k for this equation. The relationship to the original k is like this. So we'll call this double prime to represent a different equation or different k. Or I can use a different color to show you that's different k. Does that make sense? Okay, I think some of you are getting a little confused with that. So just as I mentioned before, if I look at this, A changes to B and B changes to A, normally I write it as B/A. This is my K, okay? If I manipulated this value here, I put a 2 in front, a 2 in front. That means it is 2 squared, B squared and A squared, which means it is K squared. Does that make sense? That is the same thing if I decided to put 1/3 in front instead of 2. This just becomes to the 1/3 power, 1/3 power, 1/3 power. Everyone's on the same page so far? Okay. Now let's go ahead and take a look at this example using the second one. Yes. We assume that this relationship right here is 1/3 compared to what this one is. That is why we did 1/3 in front of each of those, and it becomes k to the 1/3 power. Now, if I look at this equation right here, so we're not looking at that one anymore. What is the relationship of this equation to the original? Okay, 1/2, that's the magnitude of it, right? So this is essentially 1/2 of the original compared to this. It's 1/2, right? So if I just go ahead and put the 1/2 in here, my k should be to the 1/2, okay? So I have b 1/2 over a 1/2. So the 1/2 is the same as if I wrote the square root. So we have this part down. Everyone's on the same page so far? Okay. Now I'm going to go ahead and flip the scenario. Instead of writing A changes to B, I have here B changes to A. Okay. So now I'm going to go ahead. And once again, I'm still going to include the 1/2 here. They're all 1/2. So this one right here, in relationship to the original equation, is 1/k. Then because we have the 1/2s, I put the 1/2 in there. Does that make sense? I'm not sure where you're getting the 1/4 from.
So whenever you're making ammonia, right? So it's going to be 1/2 or K up to the third power, to the 1/3 power. But whenever you're breaking apart ammonia, it would be 1/K to the second power, to half power.
I think
mean,
you're
whenever you're
mistaken on what
breaking-
we're referring to.
Right.
This is the equation for ammonia in general.
Correct.
If you happen to have this equation, you're relating this equation to whatever the original one is. Does that make sense?
Yeah, I get that. I'm just curious to know, is that a rule that whenever you have the ammonia and the equation is like equation B, which is breaking apart ammonia, so relating it to the original equation, it would be 1/, because it's breaking it apart, as opposed to equation A, which because it's forming ammonia, it would be K to whatever power it would be.
I see what you mean. Yes. So if this was exactly just flipped around, just as we mentioned, B changes to A, then yeah, it would just essentially be 1/k. Now remember, K is a constant. This doesn't mean that K is going to be a value that doesn't exist. So they both have numbers. Okay. So it's going to be essentially 1 over this number. So one reaction is going to shift more in this direction, the other one's shift more in the other direction. Okay. So if we look at our K value here, this is a very small number, right? So we produce a small amount of this. We tend to have more of this. Okay. If you flip the scenario, ammonia tends to break down more into N2 and H2. Does that make sense? Okay. All right, let's continue. We can go ahead and look at the answers here. Again, reference point is referring to the original one. 1/3 of the original gives you that answer right there. That is essentially cube roots. And the other one is 1/1/2. It's the same as if I wrote the negative. Okay, any questions so far up to this point? All right. So just as we mentioned before, when we're talking about heterogeneous mixtures versus homogeneous mixtures, homogeneous mixtures means that they have the same phases. So we're looking at all gases or all aqueous solutions. Heterogeneous mixtures, you can see from here, there are different phases involved. So I have gases and solids here. Now we know that these remain constant, so they don't change. So we don't have an equilibrium expression. So they remain the exact same. We don't have to worry about it. This is the only one we include in our equilibrium expression. So all solids and liquids are left out. So our expression should look like this. Any questions? Okay. So this is just a good summary of all the ways of expressing Q and K that you've learned about. Once again, you can find this on table 17.2. I won't spend too long on this. You have all your reference points and the relationship between them flipped around. This is the example that we spoke about earlier. And then we have other examples where you factored in a difference of a coefficient of n. Okay. Any questions? Okay. So the next thing we're going to talk about is you're going to see these little symbols where you see KC, KP, K whatever. This is referring to the type that we're looking at. So they're still equilibrium expressions, but for KC, it is based on concentration. KP, it is based on pressure. How many of you remember the ideal gas law? Okay, what is our ideal gas law? PV equals nRT, okay? Now, if you go ahead and move V to the other side, and this is gone, N over V is the same as if we were writing our molarity. Okay. Our molarity is the same as our concentration. I'm just going to go ahead and cross those out. So the pressure is related to the concentration times RT. So it's very similar to this equation over here. Your pressure is on the left side, concentration is over here multiplied by RT. The most important thing to pay attention to is this delta N. So the change in the moles of gas. If the moles of gas change equals 0, right? RT to the 0 becomes 1. So once again, if there is no change in the moles of gas from the left side to the right side or vice versa, this can go into 1, and then Kc and Kp are equal to each other. You always want to find a scenario where that is the case. Sometimes it's not. In this case, you have 2, 3 in total. Here you have 2. So that does not match. So your delta N here is actually going to be -1. Any questions so far? Okay, let's continue. Just as I mentioned with the PV equals nRT, N divided by V will give you molarity, which is your concentration. Okay, go ahead and take a minute, see if you can go ahead and calculate this equation right here, using that information that you learned about Kc and Kp. Okay, what did everyone get as their delta N, or the change in the moles of gas? Should come out to 1. Okay, you go from 0 to 1, so it should be a +1 because the change is a positive value. Okay, knowing that, let's go ahead and set up our equation. We plug everything in. We know that it is a value of 1. The original equation has Kc and Kp flipped here. So if you want to get Kp onto this side and Kc onto the other, your N just becomes -1. And what's essentially happening is you're taking this and moving it to the other side here. So this becomes Kp over RT to the 1 power. And if you do that, it's the same thing as if you did -1 because it's on the bottom. Okay. Any questions on how to get this answer here? Okay. So let's continue. This slide. Okay, you got it? So this is 0 and this is 1, right? So this is my before, this is my after. You always do your final minus your initial. So if my final has 1 and my initial has 0, this comes out to 1. Now, with that said, we go over to here. The reason why it is -1 is because we moved the RT delta N to the other side. So in case anyone's confused about that. Okay. So we're going to go ahead and determine the direction of our reaction based on the relation between Q and K. So remember, Q is where you are at that moment, wherever that is. K is a constant, it does not change. So if Q is less than K, that means my ratio of products over reactants, I either have too much reactants or too little products. Some combination of that sort. I don't have enough products or have too much reactants. So it's not enough to reach K. So as a response, in order to react to this and shift to reach K, we will essentially use up our reactants and make more products. So in other words, shifting to the right. So we're taking our reactants, we're changing it into products. Okay, so this is a shift to the right when Q is less than K. When Q is greater than K, this means that my ratio of products with reactants, I have too many products, too little reactants, because the number is too big. So as a response, I am going to go ahead and use some of my products and shift it into my reactants. It's going to shift this thing to essentially adjust so it reaches K. And once we have them equal to each other, we are at equilibrium. It is good. There is no further shift. Now, this doesn't mean that the reaction stops. So once Q reaches K, there is still an exchange. So A is still changing to B and B is still changing to A. It constantly happens. It's just that the rates are now equal to each other and you cannot see a difference. So to give you an example, if me and another person are exchanging money, I am handing them $10 bills. They are handing me two $5 bills. We are continually doing this exchange. Even though the rate of exchange is the same, we are each handing each other $10 worth of money. And so neither of us have gained more money or less money, but the rate is the same and we are constantly exchanging money. So this is when we are at equilibrium. Okay, anyone have any questions so far? Okay. Now, just to give you a visual diagram, when Q is less than K, we are shifting to the right. When Q is greater than K, we're shifting to the left. If you're having trouble remembering this, I want you to imagine this as a Pac-Man. So you can see this one is going to eat in this direction to the right. This one's going to eat in this direction to the left. Okay, so imagine these less than and greater thans as your Pac-Man, if that helps you. Okay, anyone have any questions before we continue? All right. Now go ahead and take a minute. Looking at these diagrams, you're going to look at each blue dot, each red dot, that each represents something. Using that information, I want you to go ahead and determine what the Q value is for each one of these here. Okay. And then I also want you to go ahead and calculate what the K value is, and then we will talk about which way they will shift. So give that a try. Okay, so what we're going to do here first is, based on the information that you see right up here, how many A's and how many B's do I have? I'm not looking at any of the pictures here. We're not looking at that yet. Just up here. How many A's, how many B's do I have? One of each, right? So B over A is going to be my equation. So K is equal to B over A. Plug in these numbers and tell me what you get for K.
Professor,
Yes.
why B over A?
So when we go back to equilibrium expression, it is your products over your reactants. B
Oh,
is
okay,
your
okay.
product. This is your reactants.
Yeah, I see it now.
All right. So tell me what you get when you solve for this. If it makes it easier, cross out the 10 to the negative 4 because they both have 10 to the negative 4. So what is 1.2 divided by 2.8? I'm not sure how you got 4.28 times 10 to the negative 9. We're dividing. Yep. So 0.43 is our K. Okay. I want you to remember that number now. Any questions so far? Now, looking at each one of these dots, if A is red, B is blue, set up that same ratio and tell me what you get for Q. So for the very first one, B is on top over A. How many blue dots do I have? Okay. How many red dots do I have? 2, right? So 8 divided by 2 gives me 4. So that is my Q value. Okay. Do the same for each one of these three. Okay, by now you should have all 4 of these listed down in terms of their Q values. Okay. So let's take a look. We found that their K value is 0.43. We see that each one of these are our Q values here. Okay. Now, knowing that fact, let's put these together. For the first one, Q is greater than K. So it will shift to the left. Q is equal to K in the second one. They do not change. There's no net change. Q is less than greater than K again. So it shifts to the left. And then the last one, Q is less than K, it shifts to the right. Any questions on these?
So we basically had to solve for each one of them, and then that would be the answer. We would have the answer for all of them, not just one.
I'm not sure exactly what you're asking, but let me clarify. You were solving for each one of these scenarios, right? 1, 2, 3, and 4. And once you've done that, you compare your Q value to the K value, and then you will determine whether the reaction will shift as a response to the left or right so that Q can reach K. Does that clarify it a little bit?
Yes.
Okay. So with that said, we're going to move on to the next part of our class, which is going to be talking about ice tables. Does anyone else? Why is 4 shifting to the right? 0.25 is less than 0.43. So we are shifting to the right to reach 0.43. Remember, this is product over reactants. So I want this number to go up and I want this to go down so that this becomes a number close to that. Okay. Okay, the next thing we're going to talk about is a thing called ice tables. Oh, sorry. So you can tell just by looking at the names here, initial, changes, equilibrium. Okay. How many of you have heard of ice tables? Or if you took it in high school, they might have called it rice tables. They refer to it as reaction, initial changes, equilibrium. Okay. What we're going to talk about here, and from this point forward, including everything we did talk about in chapter 17, again, this is your make or break chapter. If you don't understand anything that we are talking about right now, you will struggle and you will most likely not pass chapter 18, 19, 20, and 21. So 5 of the chapters that you need to learn in this class, 17, 18, 19, 20, and 21, all involve equilibrium in some form. So if you don't know this right now, you are either going to fail the class or you're going to drop out of the class. So you want to learn this and know it well, okay? Okay, with that said, we already know that we have a relation between Q and K, okay? Q is where you are, K is where you are trying to go. You are trying to get to this point. To get to this point, you are either adding reactants or subtracting reactants, adding products or subtracting products, some combination of that sort, okay? There is some amount of things that are changing here. Our job is to find that change. We know the initial. Initial is essentially related to our Q. Equilibrium is related to our K. I want to know what it takes to get to this spot. That is our change. Does that kind of make sense? Take your silence as a yes. So this equation is going to be a very easy one that we're going to work with for now. Sorry, give me 1 second. So really quickly, what you see here is we are dealing with mainly this and this. I don't care about the graphite. Graphite is going to represent a solid. This is not included in my equilibrium expression. Okay. Tells me that I have a pressure of 0.458 atm as we are essentially making CO. And then at equilibrium, the total pressure is equal to this value here. So it wants you to calculate Kp. It's actually not giving you the full picture. It's giving you parts of things. And it wants to determine whether this reaction is going to shift to the right or shift to the left in order to reach our equilibrium. Okay. Any questions so far? Now, with that said, let's go ahead and set up our equation. Once I set up this, it's always called my ice table because I do an initial, change, and equilibrium. My initial, whatever values I have here, these are essentially going to represent my Q value. Whatever values I have here, these are essentially going to represent my K value. And then I have some amount that is changing that shifts from Q to K. Okay. So initially, it tells me that I have 0.458 atm of CO2 in the beginning. I have no carbon monoxide, no CO right at the beginning. It says we start with just this. We don't have any CO. Graphite we ignore, so we don't need to deal with it. By the time I am done, I know that I have a total pressure of 0.757. Now, we can look at this in 2 ways. You're going to look at the relation between Q and K to kind of determine whether we are shifting to the right or shifting to the left. If I was shifting to the right side, I'm using up CO2, I am making these, okay? So I'm using this, making more of that. If I was shifting to the left side, I am using this and making more of this. Does that make sense? Okay. Now, in addition to that, we need to pay attention to the coefficients. So if this is a 1-to-2 ratio, as I use up one of these, I should make 2 of these at all times. The ratio is going to be set in stone here. Okay, so that coefficient determines my ratio of how many x's that we are dealing with here. In this scenario, it's just 1x and making 2x in the process. Okay, so with that said, I rewrite my initial and change together. That becomes my equilibrium expression. That's always going to be the case. So these two are added together. This is just that. These two are combined together. 0.458 minus x becomes the entire equation, 0.458 minus x. So when I write my equilibrium expression, if I was to write this in terms of K, this would be 2x on top. And because this is the 2, this is your equilibrium expression squared. And it is over 0.458 minus x, your products over reactants. Does this part make sense so far?
Why is the coefficient 2 over 2x?
Why is this? So remember where we got this 2x from, right? The ratio is a 1-to-2. Does that make sense? That is why there's a 2x here. And the reason why this 2 is here, that also generates that exponent here. Going back to our equilibrium expression. Does that make sense?
Okay. Yes.
All right. No, reactant is not always negative. So just as I mentioned, in this scenario, it kind of shows us that we only have this and we don't have this. So the reaction must go in this direction, right? You can't go from 0 to something. That would be essentially negative. If you already don't have anything there, you can't make it go less. If you have something here, it's going to consume that. We can also base it off of the relation between Q and K. In this scenario, Q is less than K because you don't have any product. So this is essentially a 0. So you're shifting to the right as a response. Does that make sense?
Professor,
Yes.
if the CO was more than the CO2, then it would be going to the left.
Once again, you cannot guarantee it off of that, right? You have to compare the ratio between Q and K. If K was a number that's like 500, right?
Yeah.
And Q was a number that was 1. So if this happened to be 0.458, it would still shift to the right. Does that make sense? Because this would just be this divided by this would give me just 1, which again is less than this. So it's still going to shift to the right.
Okay.
I can use more of this and make more of the other one in the process. Okay.
Yeah.
All right. So with that said, we're going to go ahead and write our equilibrium expression. The good news about this is one of our rare occasions. The total pressure is equal to the sum of all of your partial pressures. So 0.757 is equal to this plus that. Okay. And so we can combine the two of them together. This minus x and this plus x, they cancel out. You get plus x by itself. So you can find your missing x. Once you have done that, you can find the partial pressures for each one of these scenarios. So these are your two partial pressures. I plug it into my Kp expression, and this is what I get. So you notice the 2 is still there from that CO carbon monoxide. That's still included, and we need to factor that in.
Professor, where did you get the 2x from again?
So let me go back. Give me a second. So 2x comes from this 2 right here. If I said I had A, or let's say 2A changes into B, okay? For every 2 A's that I use up, I make 1 B. Does that make sense?
Yes.
Okay, so if I take away 2 A's, how many B's did I make?
You took them away
I took away 2 A's. I used up 2 A's. How many B's did I make?
and you said that every 2 A's you make 1 B.
Yes.
So if you took away the 2 A's, you wouldn't have any B.
If I use up 2 A's, 2 of the A's, what am I making? I would have 1 B. I'm using up 2 of these. I'm making 1 of these. Does that make sense?
Okay.
Okay. So with that said, I have used up 2 A's. I've made 1 B. That's kind of the same thing that we're talking about here. Okay. I use up 1 of these in terms of ratio. I make 2 of these as a response. Do you see that?
Yeah.
So that's why we set it up this way, because we don't know how much it is changing by, but we know the ratio between the two. It's a 1-to-2 ratio.
Okay.
Okay. Okay. With that said, you should end up with your Kp value right here. Does anyone need time to copy this down? All right. Take some time to copy it down. Okay, does anyone else still need more time? No, 0.757 is just that they provided. That is our total pressure at equilibrium for this particular reaction. Okay. So let's try a different scenario. This one changes it up. We're going to focus more on concentration. Sometimes we focus on pressure, sometimes we focus on concentration. If you do pressures, you can deal with total pressures and partial pressures. A lot of the expressions you deal with here are going to be with concentration. So I'll give you a second. See if you can set up your ice table here. If you're having trouble, then I will help you out. Okay, is anyone having trouble starting this? Okay, so how we can begin this, let me just clear my screen real quick. Give me 1 second. Okay, so what we're gonna do here is we're gonna go ahead and just write our ice expression, so our ice table, okay? Copy this equation directly right above, so 2HI, and it changes into H2 plus I2, okay? Now let's read the question. So the question says that we're looking at a decomposition of hydrogen halide, so we're breaking this apart. And it says we only have this in the equation. Okay, so I have a 2-liter flask, 0.2 moles. So if I can translate that into concentration, it would be 0.2 moles over 2 liters. That should give you a total of 0.1 molarity. This is how much I have to start, and I only have HI. I don't have any of these two. So these are both 0. Does that make sense? Okay. With that said, which way will this reaction shift, right or left?
Right?
Shift to the right, because I don't have anything here. You can't shift away from this if you don't have anything. So it's going to shift to the right. If it's shifting to the right, that means I am using up this. I am making this. Does that make sense? Now let's look at the coefficients, okay? This is a 2:1:1 ratio. So this is minus 2x plus 1x plus 1x. Okay? So let me rewrite this expression down here. 0.1 minus 2x. This is just 0 and 1x, so that's just 1x. This is 1x. I can even get rid of the 1 to make things a little easier. Any questions on the setup here? Okay, I'm gonna go ahead and clear the screen now. If you need another second to copy it, please let me know. Otherwise, I'm clearing it. Okay. So they have the same exact setup. We went ahead and found 0.1 molarity. We plugged everything in to the minus x, minus 2x, plus x, plus x. We get that equilibrium expression. Now, what we're gonna go ahead and do is, the good news is it tells us that HI at equilibrium is equal to this number. So we already know this value. So at equilibrium, the HI is equal to this. And we know this is our equation with it. So we can relate the two of these together and we can solve for our x. A lot of times they won't give you this. They'll actually just give you the k value and you would need to algebraically solve for the x using whatever you have there. For the purpose of this one question right here, it's made it easier. It tells you what x is. Okay. So once we get to here, I can plug in my values for x for both of them. So this becomes k is equal to x squared over 0.078. Because this is the equilibrium expression of H2, I2 over 0.078. But keep in mind, this is for one of the HIs. This 2 here needs to end up as an exponent here, okay? Any questions so far? Okay, so let's go ahead. Why did I set this up this way? Like this?
No, why did you do K2 over the 0.078?
So let me go back a second. When you said K2, I didn't do K2, I just did K, okay? So this is x squared on top because I put these as your products. That makes
Oh,
sense?
I wrote it wrong. That's why. Sorry.
Okay. All right. So we go ahead and plug that in. It's the same thing as if I just decided to put this as x. So x is equal to that value, right? So I just plugged it in here. This is x and x. And this is the 1.100 minus 2x. And we still have to include the squared because that tells us the coefficient is here. Okay. Any questions about this one? Okay, let's continue. We're going to do a couple more of these. I want you to get used to setting up your ICE tables first. So try setting up your ICE tables. If you don't know what to do after that, I can help you with that. Okay. Always look at two things: the relationship between Q and K, and then whatever your coefficients are. So if this is A over here, you have something to the A power plus B changes into C and D. Make sure you have these coefficients down and you have the relationship between Q and K down. And if you don't have that yet, at least realize if you have one and not the other, you know which direction it will shift. So give you some time to work on this one. Okay, is anyone having trouble with this? Okay, does anyone else need more time with this one?
I need more time.
Okay. Okay, by now you should have realized that you don't actually need a full ice table for this one, because it's not telling you what your initial values are. It's telling you what it is at equilibrium. So let's go and take a look. Good news here. None of these are at initial value. They are all at equilibrium already. So we have that information, okay? The only thing you have to do is go ahead and divide it by the 0.32 liters for the container. So all of your values here are divided from moles over liters, gives you the concentration. So you have each of your concentrations here, okay? And you don't have to worry about that, and you don't need your initial value. So you have some of each, and they are all at equilibrium. So it's a very easy problem. Only thing you are missing is this one right here. And they also tell you what KC. So this just becomes algebra. Any questions? Does anyone need time to copy this down? Okay. So we have our equation here. KC is equal to all of the above here. Good news for us, right? You also need to go ahead and make sure things are balanced. Once you have balanced everything, algebraically move H2O out of this and KC into that spot. And then you can just plug everything in and solve for it. So this one is actually not one of our ice table equations. This is just telling you if things are at equilibrium, I want you to find the missing piece. How do you find it? Any questions? Okay. Now, with that said, we do have an actual equilibrium equation. I want you to try this one out. Set up your ice table, set up your equation, and then tell me what you get as far as you can get, okay? And I will help you with anything you are missing. Okay, is anyone having trouble with this one right here? All right, so what we're gonna do here, we are going to go ahead and we see our Kc value. We see that our equation involves these four things, okay? We're changing CO and H2O into CO2 and H2. Okay, so those are the two sets of equations. Tells you that we have CO and H2O, so we know the amount that we started with. So 0.250, it's the same for both numbers. And in a 125 milliliter flask, I changed that into liters. So 0.125 liters. Okay. So knowing this should give me about 2 molarity. Does that make sense for everyone so far? Okay. I'm going to go ahead and clear my screen. Let's take a look at the ice table based on that information. We have 2 molarity. I plug it into my equation. I start with 2 on both sides here. I have nothing for the right side to begin with. I don't have any of this. So knowing that fact, I know I am shifting in this direction. If I look at my coefficients and balance the equation, this is a 1 to 1 to 1 to 1 ratio. Okay. But this is minus x plus x plus x. And then we can bring that equation down, write everything down here. So I'm just going to let the computer, the screen generate all that, so I don't have to rewrite it. 2 minus x, x, and x. Any questions up to this part? Setting up your ice table. Anyone confused on where everything comes from? Okay. With that said now, I can now go ahead and do the next part. I know my Kc value. It told me that it was 1.56. And I also know my Kc is equal to x times x, which is my products on top, over my reactants. So 2 minus x, 2 minus x. Okay. Good news is because this is a 1 to 1 to 1 ratio and it's the same concentration for both, this just becomes x squared over 2 minus x squared. Okay. So I simplify this whole area into that. I'll rewrite that one a little neater. Any questions up to this part here? Okay, so with that said, I'm just going to go ahead and generate the same stuff over here. So you have that x squared over 2 minus x squared. Now, if you were to algebraically try to solve this, even though this is equal to 1.56, it would be a real pain to try to do this because you're dealing with x squared, right? You have to FOIL the bottom. You have to deal with the x on top. It becomes x squared, all these kind of things. It's a very, very complicated process. But there is something we can do to make it easier. How do I simplify this equation? The top has a square, the bottom has a squared. Not cross. If I cross multiply, it's the same thing. I'm just trying to algebraically solve for x. X ends up on both sides, it becomes a problem. You can square root. You square root both sides of these, okay? Once we square root both sides, it just becomes x over 2 minus x is equal to 1.56. Now I can algebraically solve this in a very, very simple method, okay? Does that make sense to everyone so far? If you see squared on both sides, you want to go ahead and find a way to square root this to make it as easy as possible. So we square root this, both sides. You end up with plus or minus 1.25. You plug everything in. Oh, sorry. Plus or minus of this becomes 1.25. Your overall x becomes 1.11. Any questions up to this step right here?
I'm
Okay.
sorry, where did the plus or minus come from?
So when you do a square root, okay, it can be positive or negative. So if I do square root of 9, right? 3 times 3 can give me 9. Negative 3 times negative 3 can give me 9. Does that make sense? That's why we have the plus or minus.
Yes.
So 1.25 times 1.25 gives you 1.56. Negative 1.25 times negative 1.25 also gives you 1.56. Okay. So with that said, once you find x, you are not done yet because x is only the answer for this spot right here. You need to finish it by plugging in the x for here to solve for what this becomes. So these are your equilibrium concentrations. This will be 0.89, 0.89, 1.11, and 1.11. Any questions?
What's the 0.89?
That's this. Because this is this value right here. Does that make sense?
Oh, okay, yeah.
Okay. Okay, does anyone else have any questions on this? Anybody need more time to copy it? Yes, the reactant equilibrium concentration is 0.89 and the product is at equilibrium is 1.11. Someone wanted me to go back to this slide. This one right here.
And where did you get the 1.11 from?
1.11 was algebraically solved. So go back to the front. So let's try to solve this, okay? All right, give me 1 second. Okay, right here, you take this equation right here. So x is equal to, if I move the 2 minus x to the other side, so it's 1.25, 2 minus x. Okay, I multiply this out, I do the distributive property, solve for each one. I move the x's to one side, the number to the other, you should end up with this number here. Does that make sense?
Yes.
Okay. All right. So concentrations are written at the bottom here. This is something that you would have determined once you have solved for your value of x. Okay, any questions before we continue? Sometimes they'll ask you to solve for the value of Kc. Sometimes they'll ask you to solve for the equilibrium concentrations for each individual item, things like that. So it depends on what they are asking you for. All right, does anyone else need more time to copy this down? Okay. So we're gonna try a scenario here. I have two different concentrations for you, okay? Try it with this one first, then try it with that one next, using the same format that you saw earlier. Okay, and give you some time with it to try to set up your ice table. Okay, is anyone having trouble with this? Or not sure how to set up their ice table?
Yes.
Okay, so let's try this out, okay? We'll go piece by piece. We'll go ahead and find the concentration. Remember, this was in a 10-liter flask. So 5 moles over 10 liters gives you a 0.5 molarity, okay? So this is my molarity. I set up my ice table. If you look carefully, I only have COCl2 to begin. So I don't have any of these. I know I am shifting in this direction, okay? With that said, it's a 1-to-1-to-1 ratio, minus x plus x plus x. Any questions getting up to here? Just this part. Okay, I'm assuming everyone is able to reach this part, or if you weren't previously, now you are able to, okay? Once we get to here, let's plug this into our equilibrium expression. You have KC and you have these numbers, x squared over 0.5 minus x. And you know your KC is equal to that number. We run into a little bit of a problem here. If I wanted to solve for x, it would be a big pain to deal with because I have x squared and I have 0.500 minus x. It becomes a huge number, okay? So what we do in this scenario here, I look at the value of this and I look at the value of my KC. Generally speaking, this is a very high number, okay? This is close to being 1 or higher. It's a very big number. My KC is a very small number, right? By definition, if my KC is a very small number, by the time I'm at equilibrium, should I have more products or reactants? If KC is very, very small, by the time we hit equilibrium, should there be more products compared to reactants or more reactants compared to products? Remember,
More product.
the ratio is products over reactants, right? If this number was big, then I would have more products in the process. If this number was small, then I would have more reactants in the process, or I would have smaller products, okay? So I should have, based on this K right here, a lot more of my reactants than I do products. Does that make sense? Once again, I should have more reactants than I do products. Okay, so by the time we're done, there should be a lot of my reactant, very little of my product. So I can assume that the amount that this is compared to this is very, very small. This is still going to be very, very high. Okay, so we can go ahead and make an assumption rule that the change, this part right here, let me go ahead and just clear the screen real quick. This change right here is small enough that it is negligible, that I can ignore it. Okay, so that by the time I'm done, my concentration originally starting is still closer to 0.500. I mean, I'm still going to have some amount of X. Okay, it is going to, some of it is going to leave, but I assume that the change is so small that this I can almost round to 0.500. Does that make sense so far? Based on the information that I was given here. Okay, so we're going to go ahead and remove that minus X. So this is now gone. Now, algebraically, if I wanted to solve this, it makes it so much easier. I take 0.500 times this number. I do X squared, I do square root. I end up with this value of X. This is my change. Now, I still need to apply it back in. This number is kind of close to that number. Can we agree on that?
Yes.
Take your silence as a yes. Okay. And then we know these two concentrations. This is how we can go ahead and solve for X without getting too complicated on stuff. Okay. We're assuming that the change here is negligible. It's so tiny, it's not going to be such a big difference. Now, with that said, we can use the 5% of the initial to assume this rule. So this is how much we have changed by, right? Compared to the original amount, if I multiply this by 100, this change is less than 4%. So it's less than 5%, so that we can assume that the minus X and plus X's, we can throw those out. The change is so small, we can ignore it. So this is also known as the 5% rule, okay? With that said, if you were to try this with the next one, 0.01 molarity, so the other concentration was smaller. So we plug everything in same way that we did before, nothing is different, okay? So I end up with this equation right here. Everything looks the same except for the value that I had here. It changed a little bit. That is the only extent, okay? I get to here. If I made that same assumption rule, when I go ahead and I got rid of this minus X, and I go ahead and calculate everything here, I end up with a change that is 2.9 times 10 to the negative 3. If I were to plug this back to the original equation that I got, which happens to be 0.01, this is actually a 29% change. So it is actually more significant. This change is very, very important. It changes a lot, okay? So that means I cannot use the 5% rule. I can't assume that this can be removed. This doesn't work. Now, if I can't assume that that's the situation, I'm going to have to use my quadratic equation in order to solve this. So going back to this, I must include that minus x. It is important. I plug it into my quadratic equation. Well, this is my quadratic equation. I can go ahead and use my quadratic equation and solve for my value of x. I'm going to go ahead and write the quadratic equation for you on the screen here. So you have that. You can always just Google it if you wanted to. I hope I have enough room to write this down. So right now, this is the same thing as that equation that you see right here. Okay? ax squared plus bx is equal to plus c is equal to 0. So the equation you will use to go ahead and solve this is equal to negative b over here. Give me 1 second, just finishing this up.
Wait, it's plus C or minus C?
This one right here,
Yeah, because in the equation, it's minusing.
that's fine. So if it's
The-
minusing this, again, you just put it as a negative of that value. That's fine. It's the same thing. So it's the same as if I wrote plus negative 7. Minus 7 is the same as plus negative 7. So you treat it that same way. That makes sense? This c itself would just be this value right here. Does that clear it up a little bit? Okay, so you would use the quadratic equation over here. You plug all these numbers in, solve for your x. Sometimes they give you 2 different x values. That's what you get, okay? And then you go ahead and plug everything in, go back to the main equation, figure each of these individual equilibrium expressions out. Does anyone need more time before I continue?
Can you go back to where you showed the 5% rule?
Sure.
I have a question. Oh wait, this probably what
This
the
5%
person
rule right
that
here?
just said.
Yeah.
Okay. Matthew, you had a question?
Oh sorry. I was gonna ask when can you assume that x is negligible? And this
If
is
it
probably
falls within this range right here, if it's less than 5%, then it is negligible. So the change, so you still have to solve for the change. You still have to solve for x first, okay? Assuming that rule. And then if the change is smaller than the original amount, then it is negligible and we can ignore it. If it's greater than 5%, then it's kind of something that matters and you want to include that in. Does that make sense?
yes, I got
Okay.
it.
Now, obviously, no one wants to spend their time making the assumption, going through the calculations, and then realizing that the calculation can't work, and then have to go back and redo the equation with the quadratics. Okay, so it's very. Oh, I had the drawing in here for the equation. Okay, so we have a method that we can use that can figure it out before you start all your calculations. Does anyone need more time to copy this before I move forward? Okay. So it's the same rule. It's still the 5% rule, but now it's just called the simplifying assumption. What you can do is you can take that initial concentration, whatever that one concentration is. Usually it's your A changing into your B and C, and these usually have 0, so you don't care about that. So whichever your initial concentration is, if you put that over your Kc. So just as I mentioned, remember previously we had a scenario where we had a very high concentration and our Kc was very low. There were actual numbers we can use. If A is big enough and Kc is small enough that the ratio here is greater than 400, we can assume that the 5% rule is justified. If it is not, if it is less than 400, we can assume that it's not justified. And at this point, you just need to simply use quadratics. Okay. Any questions?
Yeah, what needs to be greater than 400?
The ratio of your initial concentration over Kc.
So with that problem, it would be
Well,
the
let's try it.
0.50 over
So-
KC.
If you remember the exact number, I think it was 0.50 molarity, right?
Yeah, and then the
And,
KC
was something 10 to the -4, right?
8.3 to the next, yeah.
So just putting this in, this over 10 to the -4. 10 to the -4 is really just 0.0001. Okay? So this is already going to give you a number that's greater than 400. That make sense?
Yeah, I got it. Thank you.
Okay. If we did it the other way, I think it was 0.01? I forgot the exact number. Over 10 to the 4 ratio, this number essentially is not going to give you the value greater than 400. Does that make sense?
Yeah.
Okay. Now, does this rule always apply? I would say 99% of the time it always applies. There have been some rare occasions where I have had someone who happened to have made some kind of combination where it was close to that number. So this number was just maybe a little bit above 400, where the 5% rule doesn't apply, and we would actually have to use a quadratic no matter what. Will you get those kind of questions? Probably not. Okay. Any questions before we continue? All right. So I want you to go ahead and, using this information, try to solve for another one with our equilibrium expression with our ICE table. So we've been doing a lot of these problems. I want you to be familiar with them because everything else we do afterwards involves ICE tables. So we're going to do a lot of practice with this. So go ahead, take some time, start setting this up. Okay, is anyone having trouble setting this up? How many of you just need more time with it? Okay, give you another minute or two. Okay, so let's get started. Really quickly, you want to make sure you change all of these into molarity. Okay, that's the very first thing. Once you've changed them all to molarity, then you can calculate your Q value. You relate your Q value to the K value and determine whether this shifts to the left or right. So let's get that up. You get 4 molarity, 8 molarity, 4 molarity, and 8 molarity here. You set up your Q because you notice it's not 0 on either side. So you don't know whether it's shifting left or right. Okay. And we do know our KC value. I believe it was something very, very small, like 0 point something. You notice your Q value is very large. That means this has too much product compared to reactants. So the reaction is actually shifting to the left. So it's a little different than what we've been doing before. Okay. Anyone have any questions up to this part? Okay. Does anyone need time to copy this before I move forward? Okay. So once we've gotten to this part right here, our equilibrium expression, remember, we are going in the reverse reaction because of the relationship with Q and K. Since Q is greater than K, we know we are shifting to the left. So I am using up what is on the right, making what is on the left. Your coefficients must be included on the bottom here. So that's a 4x, this is a 1x, this is a 2x, and this is a 1x. Okay? So you get your equilibrium expression down here. Any questions on how to just get to this part right here? Okay, now that we are here, I don't need to go ahead and use any quadratics. I don't need to do any of that other stuff because they give you a big hint. At equilibrium, this concentration right here is equal to 5.56. So if this is equal to 5.56, we are just finding the difference of x. And since 4 plus x is equal to 5.56, x is equal to 1.56. And if you notice, once we have solved for our x, we are not done yet. This is not any particular concentration. I want the concentration of each of these 4 things. So in order to do that, I simply need to plug in x into each one of these equations and solve for that missing piece. Any questions? Okay. Now you notice they don't list this one right here because there's already, you already know the value. So it is just simply 5.56 molarity. Any questions up to this part? All right, does anyone need time to copy this down? All right. So just a little bit of preliminary steps. In order to solve for the stuff here, you balance your equation. You write the expression for Q if it applies. If one side is not 0, you don't know which direction it's going to shift. If one side is 0, you know you're shifting in that direction. Okay. Then you go ahead and take the relationship between Q and K. That tells you whether you're shifting left or shifting right. Next, you draw your reaction table, your ICE table, and then you go ahead and look at your coefficients. Your coefficients will determine whether you are doing minus 1x, plus 1x, minus 2x, or plus 2x, whatever the numbers are. Last, when you're trying to solve for your x itself, okay, you put in the values for your k. If you can make your assumption rule, make your assumption rule. Or if you can do something to eliminate the need to do quadratics, go ahead and do so. So the assumption rule is it should be less than 5%. You can use your value of initial A over K, and that should give you something that is greater than 400. Then you can assume that it is negligible. Any questions up to this part here? Now, with that said, one other thing I want to bring up, you always want to avoid quadratics. So we want to look for things where they give us one of the equilibrium concentrations. Okay. Or they give us perfect squares. So where you can go ahead and do the square root of them. So something times something. So let's say something squared over something squared. You can just square root that. If none of that works, then you apply your 5% rule, also known as your assumption rule. And then worst case scenario, if none of that works, then you need to use quadratics. Okay. This is generally the format. You have those three possibilities to avoid quadratics. If it does not exist, then you must use quadratics. Anyone have any questions up to this point? Okay, with that said, oh, sorry. We're not going to cover Le Chatelier's principle yet. We're going to do that in our next class. For the time being, I need the two co-hosts to go ahead and stop recording before I remove the co-host privileges. And then I will enable the poll right after that. Okay. So your poll is pretty easy. There's only 4 questions. I'll give you 4 minutes to answer them. You can go ahead and get started with them. And then once those 4 minutes are up, it'll be about 6:21. I will end everything early and then restart everything. So I know some of you have class at 6:30. So once again, I will end everything early and restart the class again, and we will go over the quiz during office hours. So I'll start office hours a little early. So about 6:22 is when I'll start office hours. I'll cover chapter 12 and 13 if you want to go over them there. Okay.
Can you record the office hours for some of us that can't make it or no?
I will try, but sometimes it does not record well.
Okay, thank you.
Okay. Philip, did you have a question?
Huh?
Did you have a question? You're unmuted.
Oh, I'm not sure how that happened.
Okay. All right. Once again, you have about 3 more minutes to answer the poll questions. Okay, you have another minute for the polls, and then we will go over them. Okay, you have 30 more seconds for the poll. Okay, I am going to close the poll now. You got about like 5 more seconds to finish up whatever you have to finish up. Okay. So let's take a look at the results. For the very first question, where do we get the exponents in an equilibrium expression? The answer is from the coefficients. The next one, when you write an equilibrium expression, it is always products over reactants. And then number 3, which phases are not included? That would be solids and liquids. Again, as I'm scrolling, you won't be able to see me scrolling, but you should be able to scroll it on your own. And then the last question, which one will cause the relationship, cause the reaction to shift to the right? That is when Q is less than K. Any questions up to this point? Aqueous is definitely in the equilibrium expression. So aqueous and gases are in equilibrium expression. Okay, does anyone have any last minute questions? If not, I'm going to close this out, open up office hours, go through the quizzes. And any other questions you might have there.
Okay, thank you so much, Professor.
Okay,
Thank you,
enjoy your
Professor.
day. I'll see you all next week.
Wait, Professor, would you post a review video of you going over the quizzes?
I will try, but sometimes it doesn't save well during office hours.
Okay.
So we'll see if it saves or not, okay?
Okay.
Because if I'm in the middle of, so when I disconnect from here, it starts to save the file from this lecture, okay? And then if I open up another one and I disconnect that, sometimes it doesn't save a second recording. So the first recording gets saved, the lecture is more important. The second one with the quizzes, I can't guarantee that it'll be saved.
Okay.
Yes, next week there will be a quiz. It's chapter 16 and 24 together.
Okay.
Could we schedule other office hours if we have class right now?
Yes, you can always schedule other office hours with me. Just let me know in advance. We can talk about it at a different time.
Okay, thank you.
Okay.
Professor, sorry, real quick. Besides office hours, is there like a tutoring center link we could go to? Because I tried looking online and I don't see one.
I don't know exactly what time they have it. What I would do is I would contact the chemistry department. They would probably know the best times.
Okay, I'll do that now. Thank you.
Okay. All right. Any other question before I disconnect?
I have a question.
Okay, go ahead.
Are the polls, are they included in our grade? Like,
They count as part of the participation and attendance grade.
okay, but
So
what
that
about
5% of your overall grade is based on you attending lecture, you attending recitation, you answering the poll questions, and your recitation instructors taking your attendance by you joining.
and does what we get right and wrong on the polls?
It
is
affects
that-
it a little bit. But most of it is just the fact that you answer the poll questions counts for the majority of it.
Got it.
So we're
Thank
talking
you.
about like out of those 5 points, maybe 2 of those points are based on how well you answer those poll questions. Okay, so if you just guess completely, at most you probably lose with like maybe 2 points in the process. All right,
Got it.
okay.